The broadcast is now starting. All attendees are in listen-only mode.
Hi, my name is Deirdre Mason, and I am with the Association of State Drinking Water Administrators. And I want to thank you all for joining us for our webinar today with USGS on changing source water quality, links to potential corrosivity, and emerging assessment tools. So for those of you who don't know about ASWA, our mission is to protect public health and the economy through the provision of safe drinking water. Our members are the Drinking Water Program Administrators from the 50 states, territories, the Navajo Nation, and the District of Columbia, who provide public water system oversight in the form of regulation, technical assistance, and funding, and also coordinate with multiple partners. So this is the fourth webinar in our series with USGS. We have these first three webinars listed here on our website. You can go back and view the recordings of those if you're interested. And then we'll have one more webinar coming up probably after the first of the year as well. So stay tuned for that. So for today's webinar, the presenters are going to provide information on the potential corrosivity of the nation's surface waters and groundwater, with implications for exceedances of lead action levels in drinking water, and tools for monitoring and for developing source water management strategies. So our presenters today are Ted Stetz and Steve Preston from USGS. And I just want to let you all know that after the webinar, we will have a video recording on our website. So you can see that within the next few days or maybe a week on the ASWA website. And just a little bit of housekeeping here. Please type your questions into the box on your webinar control panel. We are not be taking any verbal questions, and you can type your questions in at any time while the presenters are speaking, but we will wait until after they are all finished doing their presentations to answer the questions that have been submitted through the questions panel. And Patty Tocolino from USGS is going to join us to moderate the questions at the end. So with that, let's go ahead and start. And I'm going to turn the controls over here to Ted Stetz, who will be our first presenter.
Okay, thanks for that, Deirdre. I just want to make sure that everyone can see the proper screen, the one with the slide and not the notes on it. Is that true?
Yep, you're good.
Okay, thanks a lot. Well, thanks for the introduction. And today I'm going to be talking about chloride increases in surface waters and how that relates to the potential corrosivity. So chloride is important because of it has links to ecological and human health, as well as water infrastructure and drinking water quality. And as I'll show, it also relates to the possibility of lead and copper contamination in drinking water. This work is a product of the National Water Quality Assessment, something called the Surface Water Status and Trends Team, which is led by Lori Sprague and Wes Stone. What I'll be showing today was published in the journal Science of the Total Environment last year. Okay, so this issue relates to the larger topic of freshwater salinization that's been observed in recent decades. And just so we have the terminology straight, I give this talk to a lot of different groups. I just want to make sure we're all on the same page in terms of terminology. And I'll just point out that salinity and total dissolved solids are essentially equivalent expressions of the saltiness of water overall. And they're expressed as in units of parts per million or milligrams per liter. When you're talking about ocean water, it's much higher salinity, and it's expressed as grams per liter or parts per thousand. But for fresh waters, it's lower, and so it's in this parts per million unit. Specific conductance, on the other hand, is a surrogate for salinity that is based on the electrical conductance of a water sample. So both total dissolved solids and specific conductance result from the combined effects of all major ions in the water. So a change in any major ion can result in a change of the overall salinity of water. And so sometimes, in some cases, we're interested in how the overall specific conductance or the overall saltiness changes. And at other times, we're interested in the change in a specific major ion, okay? And that's going to be the case today. I'll focus a lot more on chloride, but we have to understand that chloride, when it increases, it also increases the overall saltiness of water, the total dissolved solids or the specific conductance. Salt control has been an important issue in arid regions for a very long time, and more recently, salinity increases have been observed in non-arid regions, okay, especially in snow-dominated areas of the U.S. And this is closely linked with chloride trends, which will be the focus during the presentation today. Okay, so I don't want to get into this too much, but there's kind of a history of looking at freshwater salinization that goes back a few decades. The earliest studies that I'm aware of really related to, and this is in non-arid regions, by the way. So, you know, these issues in sort of the western United States related to irrigation and so forth are not really part of this mini review here. But the earliest issues that I'm aware of will really pertain to the Great Lakes in particular. And that was, you know, some of these early studies by Sunzogny. I'm not exactly sure how to pronounce that, but it's a pretty good paper looking at predicted changes in chloride concentrations in the Great Lakes. More recently, it's been shown more broadly that chloride is increasing and salt in general is increasing in other places in the United States, okay? And so this was a paper that came out in 2005 by Sujay Kajal, who's at the University of Maryland, looking at increases in chloride concentration in rivers of the northeastern United States. And so he found that it was a pretty broad phenomenon in the northeastern U.S. to find increase in chloride. Since then, Steve Corsi, who's also at the USGS, found increase in chloride in a wider variety of streams around the U.S. And in this case, he related it more closely to urbanization. So the color of the panels relates to the degree of impervious surface in the watershed. And so these very dark red panels are places that are highly urbanized down to places that were less urbanized. And he found that chloride concentrations and the changes in chloride were really related to urbanization. And this is especially true in snow-dominated regions, okay? And since then, there's been a series of papers that have come out kind of expanding this idea and relating it to some different things. And the one I'll talk about the most today is the paper that we had that came out last year relating trends in chloride to the potential for corrosion in drinking water facilities. Okay, so I'll turn to that study right now. So first of all, I'm showing a map of chloride trends in U.S. rivers from between 1992 and 2012. This comes from a data set that was comprised of USGS data as well as data from other federal agencies, from states, from municipalities, from you know, other local areas like counties and things like that, as well as tribes. And so we wound up with a very broad data set that covered most of the United States, and we were able to identify chloride trends in 141 locations around the country. And you can see, you know, this kind of broad distribution, and the triangles on the map show you the trend results associated with that study. And what we found overall was that in about half of the sites around the country, we saw increasing chloride concentrations, and fewer than half we found decreasing chloride concentrations, which are denoted by this orange and yellow color, okay? And so one thing you can't really see on the map here are all of the, this doesn't really come out unfortunately, but there's a lot of up arrows in the northeastern United States. And so this goes along with what Sujay Kajal had found and Steve Corsi also identified, was that in these snow-dominated regions is really the places where we found the most, the highest increases in chloride, okay? But beyond that, you know, chloride doesn't necessarily stand out as being an element that has really these, you know, broad upward trends throughout the country. But when we start breaking it out by land use, you see something very different, okay? So here I have box plots of the change in chloride concentration between 1992 and 2012. And so anything above this line indicates a place where you found, where we were finding increases, and below the line are places where we're finding decreases. And so what you can see is that in agricultural regions, in mixed areas, in undeveloped areas, we found kind of this mixture of increases and decreases with an overall tendency towards basically no change. And the exception is the urban areas, which showed really very astonishingly high increases in chloride throughout that period of 1992 to 2012, okay? And, you know, if we go to urban areas and we think about what's contributing to these increases in chloride, these are things that have been described before, and they're not really that hard to understand. I mean, there's sources of road salt in many areas that are related to this increase in chloride concentration, and point discharges as well tend to be very high in chloride. Okay, and so people are just a very sort of salty species overall, and so a lot of what we use in our household products tend to be salty. Soaps tend to be salty, our foods are salty, etc. And so our wastewater also tends to be salty. And those are part of the contributing factors to this increase in chloride in urban areas that we've discovered. Okay, so if we think about the linkages between chloride concentration and water quality, there's really two issues that stand out. The first is that elevated chloride concentrations have adverse effects on aquatic organisms. Acute toxicity occurs at a very high concentration of 230 milligrams per liter of chloride. But this can actually be exceeded for periods of time in urban streams and snow-dominated areas. And this has been shown with high-frequency observations of specific conductants related to chloride in urban streams in St. Paul and in Milwaukee. An elevated chloride concentration can also promote corrosion of water infrastructure, and I'll talk a bit more about that. So, this group, I'm sure you are well aware of this, but I'll just go ahead and say it anyhow, but corrosion in water distribution systems is a very expensive problem overall. We estimated that $36 billion is spent annually in controlling corrosion. And as we've been discussing, it's also an important factor in drinking water quality. And controlling corrosion is one of the primary mechanisms for controlling metal contamination of drinking water, okay? And so if we think about the steps that are taken to actually control corrosion, it's to minimize all of the factors that can cause corrosion within the distribution system. And so this, includes, there again, I'm sure everyone here is well aware of this, but it includes controls such as carbonation and decarbonation. Soda and lime additions can promote scale formation. And more recently, there's been an uptick in the use of corrosion inhibitors, things like silicate, orthophosphate, and zinc orthophosphate. I saw a study recently looking at the United Kingdom saying that upwards of 90% of the drinking water facilities there were using orthophosphate as a corrosion inhibitor. And the recommended dosages of phosphate are actually quite high. So they're in the range of 1 to 3 milligrams per liter of phosphate throughout the system. And I'll come back to this a bit later. So, if we turn our attention to lead contamination, which is one of the issues related to corrosion, I think the public sort of writ large tends to think of lead contamination of drinking water as being a problem of the past, okay? And there have been great strides in controlling corrosion and lead contamination in drinking water, but this is something that is actually is ongoing even now. And just a quick search of the news as of about a year ago, I found a number of cases throughout the country where lead contamination had been reported in drinking water. And this includes a study in New York and New Jersey that found that more than 200 facilities had experienced elevated lead contamination and elevated lead concentrations in their drinking water, okay? So, I think after the issue in Flint, Michigan, the problem of lead contamination really became more in the public consciousness. And since then, that's part of the reason in the uptick of the stories since then. But if you go into the EPA databases and you look, there's actually been about 3,000 instances of elevated lead concentrations since the early 90s, okay? So that's an average of, what would that be, about 150 a year or something like that? So there's actually quite a few violations even to this day, and so it's something that is still with us, unfortunately. So the USGS has began conducting studies on the potential corrosivity of source waters in the U.S. The first study looked at the corrosivity of groundwater in the U.S., and this is important because private well owners are not subject to the same kinds of oversight as public water utilities. And so treatment for corrosivity tends to be up to the private well owner. Nevertheless, those groundwaters can be corrosive. And in fact, this study published by the USGS found that there was a high potential for groundwater to be corrosive in over half of the U.S. states. The other study is going to be the major focus of the talk today, and it's looking at surface waters, and in particular how the potential corrosivity of surface waters has changed over time, as well as some seasonal and regional patterns in corrosivity. And I'll come back to this a little bit later, and I'll talk about some of the tools and online resources that the USGS has also made available for these. Okay, so when we talk about potential corrosivity of surface waters, we're going to be focusing on a couple of indicators. And so for the purpose of this study, we'll focus on two indicators. One of them is the chloride to sulfate mass ratio, which is just what it sounds like. It's simply the ratio of chloride to sulfate concentrations in the source waters. And the second one is called the Larson ratio, which is the ratio of chloride plus sulfate over alkalinity within the surface waters. The chloride to sulfate mass ratio has been linked to lead and copper corrosion, and it acts by promoting galvanic corrosion. And galvanic corrosion occurs when two dissimilar metals are in contact. And so this is most important in systems that have had partial lead service line replacement. So the pipes made of two different metals come into contact with one another. And it can also happen when lead-containing solder is in contact with copper plumbing. And this is probably a more common situation overall. The Larson ratio, on the other hand, expresses a potential for water to cause the corrosion of iron and steel. And so, as you can see, the trends in individual major ions, as well as their ratios, can be very important to determining the overall potential corrosivity of surface water and how it can affect drinking water quality. And just so I think, you know, we're all on a similar page here, so we have a sense of the magnitude of these indicators that's important. A chloride to sulfate mass ratio of greater than 0.5 has been shown to promote corrosion in drinking water facilities. And when it gets above 2, there's a phenomenon where it can actually be difficult to control corrosion through sort of conventional means. A Larson ratio above 1, on the other hand, promotes the corrosion of iron and steel. Okay, so in the study I'll be turning to now, we looked at both the status and the trends of indicators of potential corrosivity, and especially I'll be talking about the chloride to sulfate mass ratio. The main difference between the trend analysis and the status assessment is that a status assessment describes the conditions over a fairly short period of time. So the data requirements are not as stringent, and we gain lots of sites and spatial coverage that way, okay? And so I'll be talking both about the trend analysis, which is looking at change over time, and the status assessment, which is looking at just conditions over a very short period of time. And I'll be turning to those in the next couple of slides. Okay, so coming back to something we looked at before, you know, when we looked at this map and pie chart earlier, it was expressing the change in chloride concentration. And in this case, I'm looking at changes in chloride to sulfate mass ratio between 1992 and 2012. So again, we have a map that's expressing both the upward and downward trends. There's this collection of sites in the northeastern United States, which tend to all have upward trends. And we can see from the pie chart that in this case, about 3/4 of the sites considered have some evidence of increasing chloride to sulfate mass ratio. I'll also point out that, you know, because we have a different set of data requirements, we actually have fewer sites now than we did for chloride. So in this case, the sites had to pass data screens for not only chloride, but also sulfate. And in that case, we wound up with fewer sites overall. And similar to what we saw for the chloride concentrations, for chloride to sulfate mass ratio, there's a very big difference in sites depending on the kind of land use that they're in. So again, agricultural, mixed land use, and undeveloped sites had, you know, little to no trends over the period 1992 to 2012, whereas urban sites saw these very large changes in chloride to sulfate mass ratio. Now I'm looking at we're looking here at the status assessment, and this is pertaining to a much larger number of sites. Okay, so this is up to about 250 sites around the country. And again, we're breaking the sites into different land use categories, and I'm expressing sort of the central tendency of the chloride to sulfate mass ratio within those different land use categories. Okay, and we're looking at it overlaid on those important markers of chloride to sulfate mass ratio that we looked at earlier, where anything above 0.5 tends to promote corrosivity, and anything above 2 can actually become difficult to control corrosion. And so what we see in this case is that the urban areas, once again, in addition to having these large increases in chloride to sulfate mass ratio, they also overall have just a higher chloride to sulfate mass ratio. And so this does point to a very important difference in the more urbanized areas versus not, in the sense that they tend to have more chloride, higher chloride concentrations, and those concentrations are increasing fairly rapidly, and they're leading to greater overall corrosivity in those waters, or potential corrosivity. My presentation is crashing at the moment.
Oh no, it's still showing on the screen with your slide on the status assessment. Are you able to move forward?
No, oh, there we go. Seems like it came back now. Okay. Okay, and so now we'll turn our attention to a couple of individual sites. So, you know, before we're looking at everything on a national scale, and we're breaking things into these very coarse land use categories, but I think looking at a few individual sites really helps us understand what's going on as well. And in the paper, we presented a lot more different sites and looked at some different patterns in their potential corrosivity. But it's helpful, I think, just to even look at two of these sites and look at the difference. Okay, so we'll start by looking at the Connecticut River at Thompsonville, which is in the northeastern United States. And what we're looking at here are all of the individual, these dots are the individual observations of chloride to sulfate mass ratio over an annual cycle. And so at the on the x-axis are numbers that correspond to the month of the year, so that January would be 1 and December would be 12. And we're also looking at the central tendencies, or a low S smooth of those observations over time. And so what we can see from the Connecticut River is that, first of all, we notice that, you know, almost all of the observations are way up in this range above 2 for chloride to sulfate mass ratio. The second thing we notice is that the chloride to sulfate mass ratio is highest in the winter time, okay, which is consistent with this idea that road salts associated with these winter storms is driving part of this trend that we're looking at. But there's also something that's very interesting, which is that in the summertime, in late summer, we also see a sort of a secondary increase in chloride to sulfate mass ratio. And this could result from a few different phenomena that both are quite important, I think. The first is that during late summer and early autumn is probably the low flow time of the year for the Connecticut River. And in that case, it could be that point discharges, so things like sewer outfalls and so forth, could be a higher proportion of the total flow. And that might be part of the reason we're seeing these elevated chloride to sulfate mass ratios in the late summer. The second phenomenon that it could be related to this is that the groundwater itself could be somewhat contaminated with chloride and could be leading to these elevated chloride to sulfate mass ratios in late summer. So that, you know, the other thing that will happen in low flow periods is that groundwater will become a larger part of the overall flow. And it has been demonstrated in places around the country that groundwater is becoming contaminated with road salt. And this could be the case in the Connecticut River, where we're seeing sort of a late summer phenomenon of increased chloride to sulfate mass ratio because of that. Okay, so that's something to really watch. The other thing to notice is that, you know, because these chloride to sulfate mass ratios are high for most of the time, you have to think that the drinking water facilities that are in this area are already attuned to this problem, and they are already aware that this is an issue, and they are doing something to try to control it, even though it seems to be getting worse over time, okay? And that leads us into our next example, which is in the Platte River in Louisville, Nebraska, which is a very different setting. It's out on the Great Plains, it's much drier, and it has a much larger watershed area. In this case, what we're seeing is that the chloride to sulfate mass ratios tend to be quite low in most instances, okay? And this is true throughout the year. If anything, they're a bit higher, excuse me, in late summer and early autumn, okay? And they tend to be, below 0.5 and certainly below 1 most of the time, with an exception. And that exception are these few very high chloride to sulfate mass ratio values that we see in late summer, early autumn. These all occurred in 2012, which was an exceptionally severe drought in that area, okay? And so this is a case where the chloride to sulfate mass ratio is being perturbed by a hydrological phenomenon, okay? So in this case, there's a drought that is influencing the relative input of water from some of the upstream tributaries and is leading to this somewhat unexpected increase in chloride to sulfate mass ratio, okay? So while the chloride to sulfate mass ratios are typically quite lower and they're presenting a different kind of an issue for the drinking water facilities, these couple of observations that are high can be actually quite problematic, okay, in this type of region. And it's something else to watch out for, is that, as the climate changes going forward, and that, in some areas we'll be having more exceptional droughts more frequently, this type of a phenomenon is something for sure to watch out for, okay? Okay, and I think this type of a slide really emphasizes there again the importance of monitoring to understand when potential corrosivity may be highest and what's driving it at any individual location. And so, these national scale patterns that we can pick out have to be understood that in the context of local scale phenomenon that are overlaying on top of it. Okay, so now I'll talk about one additional analysis included in this study, and this looked at the linkages between surface water quality and the occurrence of lead action level exceedances at a drinking water facility. So an action level exceedance is a violation of the lead and copper rule by a drinking water facility, and it's defined as a situation where the 90th percentile of tap water samples is above the 15 parts per billion lead concentration. So in other words, 10% of the samples were above that limit. And when this occurs, the drinking water facilities are supposed to report this to the EPA, and it's entered into a database called the Safe Drinking Water Information System. And so our approach was to define watershed boundaries for all of our water quality trend sites, and then to locate all of the surface drinking water intakes upstream of the sampling location. We counted the total number of action level exceedances in the basin, and then we related this to the water quality at the sampling location. Okay, so the basins were required to have at least 5 intakes, and they were also limited to a size of 30,000 square kilometers. And we did this to make sure that the water at the outlet of the basin was indicative of the water quality at the intakes as well. Okay, so when the basins get too large, there's no guarantee that what you're seeing at the outlet will be the same as what's at any particular location. Okay, and then we looked at how the number of lead action level exceedances compared to the chloride concentration, the Larson ratio, and the chloride to sulfate mass ratio. And here we're looking at the average, at the site average chloride to sulfate mass ratio on the x-axis. So this refers to this the monitoring location at the outlet of the watershed. And then we're counting up how many action level exceedances we have per 10 drinking water intakes within the basin. And we find this kind of messy relationship that seems to indicate an increase in the probability of finding an action level exceedance when the chloride to sulfate mass ratio is quite high, okay? And one of the things that makes this kind of an analysis difficult are these large number of basins that didn't have any observed violations of the drinking water, the lead and copper rule, okay? So a high number of non-detects like this required us to use something a little bit different. And so instead what we did was a logistic regression that asked what the probability was of finding an exceedance in the basin given a different chloride to sulfate mass ratio. And in that case, we found a very strongly significant, although highly variable relationship between the probability of finding an exceedance and the chloride to sulfate mass ratio, okay? And so this study, I think, was quite significant because it was the first one to really tie source water quality to the possibility of finding a lead action level exceedance within the drinking water facility, okay? So all the studies I'm aware of up to this point have dealt with the finished water, the water that is inside the system already, and looking at the chloride to sulfate mass ratio there and relating that to lead action level exceedances. But this actually goes a step further and relates it to the surface water quality. And as we've seen, the surface water quality is changing quite rapidly in some areas. And so this is something to be aware of, that there is pretty good evidence that there will be a change in the probability of finding a lead action level exceedance as water quality continues to evolve in these rivers. Okay, so just to recap the major findings of this study, we saw large increases in chloride concentration and chloride to sulfate mass ratio, particularly in urban areas over the period 1992 to 2012. In addition to the long-term changes in potential corrosivity, we also observed some really important seasonal patterns that were different depending on the location where you're actually doing the monitoring. And third, we found a statistical relationship between potential corrosivity of surface water and the probability of finding a lead action level exceedance at the tap, okay? And so that, I think, was a very significant finding by itself. So the implications are that monitoring of the critical elements, for example, chloride and sulfate concentrations, will be needed to optimize corrosion control. The trends suggest that potential corrosivity is likely to become worse in certain areas in the future, and that there will be effects of increased corrosion control. You know, something as, someone who's interested in water quality, I think about this a lot. What is the increased orthophosphate inputs to wastewater treatment plants going to do to overall water quality? And does this also, in some cases, lead to increased zinc loading because zinc orthophosphate is used at times as a corrosion inhibitor? Okay, and then I'll just leave you with some resources. This is a screenshot of the online water quality trends mapper, and I'm not going to do a demonstration here, but I'll encourage you to take some time to look at the interface and see what it can do. It's a pretty nice application. You can use it to explore trends in nutrients, sediments, major ions, and specific conductants in streams of the U.S. The analysis period covers 1972 to 2012. It includes data from a wide range of partners, as I mentioned earlier. And the link is at the bottom of this slide, okay? And I can also send it to anybody who's interested. We've also developed a tool that allows exploration of groundwater status and trends in the U.S. The locations shown on the mapper represent well networks that were sampled at multiple time periods over the past 30 years. Trends in these were determined as step changes in concentration at the well networks. The example map that I'm showing is for chloride trends between the first and second sampling periods, which covers the time period 1988 to 2013. Trends for other constituents and other time periods are also available on the mapper. And this is the link to it at the bottom of the page. And again, I'm happy to share this with anyone as well. Lastly, I'll leave you with some links to some other resources, including myself, if anybody wants to get in touch with me. And that's all I have for today. Thank you.
Great. Thank you so much, Ted. And our next presenter is Steve Preston. Steve, are you ready to go?
I am.
All right. If you could just hit F5. There you go.
Is that good?
Yep.
Okay. So I'm going to follow up with Ted to describe some new models and new modeling tools that may be of interest to this group. Much of what I'll be describing is based on Sparrow modeling, which provides spatially explicit estimates of a variety of water quality characteristics. Some of the new models that we've developed recently and the modeling tools are relevant to drinking water supply. And those constituents include water balance models, looking at volume in the stream as well as total dissolved solids that's related to salinity, as Ted described, and suspended sediment models. So I'll start out just by going through a list of the models and tools that I'll describe. In recent years, we've worked on developing new models for 5 large regions of the country covering the full conterminous US. We're very close to having those published and released now, so they'll be coming before very long. As part of that effort, we've developed a large number of national geospatial databases, and we're in the process of publishing those as well. I'll touch on a few of those that may be of interest to this group. I'll also describe new web-based mapping tools. Those are associated with each of the models so that anyone can access the model results and explore them for themselves. And then lastly, I'll describe briefly a couple of other modeling efforts focused on assessing benchmark exceedance probabilities in a spatial context. I'm losing my voice here, I apologize. All of these tools are relatively new, and in fact, not all of them have been published as yet. We expect all of them to be released in the near future, and so we really just wanted to make you aware that these things were coming. So the modeling framework that we use is known as Sparrow, which stands for Spatially Referenced Regressions on Watershed Attributes. Sparrow is known as a hybrid model in that it's process-based, but it's built in a statistical framework so that all the algorithms, theory, and diagnostics that come with advanced statistical techniques are available for modeling. At the heart of Sparrow models is the principle of mass balance, in which sources of contaminants are weighed against losses to optimally predict the mass measured at specific stream locations. To build a model, we start with stream loads estimated at as many sites as possible throughout the spatial domain. I'm going to use nutrients as the example here, but those stream load values are related to various types of geographic data that describe sources like fertilizer application and wastewater discharge, and landscape characteristics that affect delivery like soils and precipitation. The monitoring data and the geographic data are all linked in the same spatial framework, which is defined by a stream network data set. And once all that data is combined in the spatial framework, the model is calibrated to optimally reproduce the measured loads at various locations. So once calibrated, the model can be used to predict annual loads at every stream in the entire spatial domain. Nationally, depending on the resolution of the data set, that can be anywhere from 64,000 stream reaches up to 2.5 million, depending on the data set used. For each of those streams, the models are used to estimate water quality predictions for things like constituent load, yield, or concentration. And each of those estimates can be developed on a total basis due to all sources, or the effect of individual sources can be isolated so that you can explore the role of individual sources separately. So the monitoring data are key to developing Sparrow models, and so we put a fair amount of effort into compiling as much stream load information based on monitoring as we can. Monitoring data are the eyes of the water quality model, the way we think of it, in that the model predictions will reflect what the monitoring data represent. So for that reason, we put significant effort into locating and incorporating as much monitoring information as possible, including any data from federal, state, or local monitoring programs. The result of that effort for these models that you see here is that we were able to gather enough data to calculate loads for 2,700 sites, and that included data from 73 different agencies. To develop the load database, we start out with the national databases, including the USGS NWIS system and the EPA STORET system. But we also made numerous contacts with regional, state, and local monitoring agencies to obtain data that wasn't included in those national databases. The challenge of all that is that there's quite a bit of I'd say, inconsistency in how the data are reported and documented. That limits what you can do with much of the data. And so it also limits the usefulness of that data as well. And so that illustrates the need for greater coordination among monitoring agencies and for organizations like the National Water Monitoring Council. So this is just one example of the types of predictions you can get from the models. The map on the left are indications of nitrogen yield in this case. The darker areas representing those areas where the higher yields are located. These are local yields, which means to each individual stream reach. And there are 240,000 predictions included in that map. So the largest area of high nitrogen yield is in the upper Midwest, but there's other areas of high nitrogen yields, such as in the Pacific Northwest, the Gulf Coast, and in the Mid-Atlantic. The map on the right illustrates the regional estimates of the largest source of nitrogen to each of those stream reaches. And you can see that it gives a good indication of where individual sources are most important. So together, the two maps give a pretty complete picture of where nitrogen is highest and what the dominant sources are. The upper Midwest, it's clearly agriculture that's the dominant source, but interspersed in other areas of the country, urban areas and point sources are the dominant sources. I'll show a couple examples of how this information has been used in management decisions. The first is that it provides a complete inventory of estimates of water quality conditions throughout the spatial domain. So in this case, this was a national model. National agencies like EPA can get a full idea of the range of conditions and what the expected amounts are in streams anywhere. But that area can also be subsetted so that any watershed or region or state could be pulled out to evaluate conditions in that region as well. The models can also be used to estimate what areas are contributing to downstream locations. In this case, this is the Mississippi drainage, and everything is linked to the mouth, and the highlighting indicates which areas are contributing the most to the mouth of the Mississippi. As I showed in that previous slide, you can isolate out and apportion each of the model predictions to individual sources so that you can evaluate what the role of each of those individual sources are in the overall downstream loads. The models have been used for targeting purposes. In this particular example, We had agricultural agencies contact us in the Chesapeake Bay watershed. They wanted a basis for allocating resources for implementing management practices, EQIP funds in particular. So we identified those drainages that were contributing the most to Chesapeake Bay for both nitrogen and phosphorus, and then also for both nutrients. And those agricultural agencies used that in their decisions about where to place resources. The last one is that the models can be used to evaluate change scenarios. Things like the implementation of management practices, what's the downstream benefit of doing things like that, as well as landscape changes and that sort of thing. Okay, so all of those slides I included mostly for background to explain what the model is. They're all based on a previous generation of models that we published in 2011. We've moved on now to develop a new set of models with a number of improvements, and I'll go through kind of a list of the major improvements that we've done. The first is that we've developed regional models for 5 regions that cover the full conterminous US. That previous set of models, we did not do the Southwest, mostly just due to resource constraints. And so this time around, we have it for the whole US. We've shifted our stream network data set to one that's much higher resolution. The previous models, actually, I'll talk more about this in an upcoming slide, but NHD Plus is the new network, and that has significantly more spatial resolution over what we used before. We have improved the geospatial data set significantly in a number of ways. The big challenge in modeling really is to build the data infrastructure for modeling. At the national scale, data sets are often incomplete or limited, or in large part non-existent. And so we often have to go in and build data sets that that are representative of the factors that we want to consider in the models. So that's really almost the largest part of this model building exercise, is building those data sets. And then for this go around, we modeled for 4 constituents, including water volume in the streams, nutrients, nitrogen and phosphorus like before, and then suspended sediment as well. And we now have all of those models completed. We're in the process of publication, and we expect to have that completed in 2019, probably the 3rd quarter of 2019, and they should be available at that time. Okay, so I'll shift gears a little bit and just talk about a couple of examples of the geospatial data work that we did. Start out with talking a little bit about the stream network data. The stream network forms the spatial framework of the models, and it's defined by stream lines that determine the connectivity and flow direction up and down through the network. Those are broken into segments we call reaches, and each of those individual reaches has an individual drainage defined, which we call a catchment. The data set we have been using is known as RF1. That's an EPA data set, and it's got about 64,000 reaches nationally. The one we've shifted to is NHD Plus, which has significantly greater resolution, and it's got more than 2.5 million stream reaches. And this is just one example of the difference in resolution. This is for New England. You can see some fairly big gaps in the coverage there, and so it's a big benefit to get this new data set. So I'll just describe a little bit about the complexity in dealing with these data sets. The limit of NHD Plus is that it's a less mature data set compared to RF1. In other words, it still has flaws and errors and limitations. And this slide illustrates just one example of that. We did a fair amount of QA to try to detect any errors we could find. And one of the things we did was compare documented drainage basin sizes at gauges, like this one up here, to ones that were defined by the network. We saw a big gap here, and what we found was that the network had a diversion so that the drainage area was only being defined by this little area. So we had to go in and find out why that was happening, and it turns out the flow direction on this creek was reversed. So what that means is you actually have to go in and reverse the direction on all of the connecting stream reaches all the way back up, so that the integrity of the network is restored. This is just kind of one illustration for just to kind of indicate what needed to be done. We made lots of changes like this, corrected errors where we could find them, but we also enhanced stream reach attributes, like adding known withdrawals and discharges on the network and identifying impounded stream reaches. And then we also linked all of our geospatial information to the network so that each catchment had a value for a variety of landscape characteristics like land use and a variety of other variables. Another data set that we put a fair amount of work into was the point source discharge data set. Point sources are really our strongest predictor of water quality conditions in the network. And for that reason, we put a fair amount of effort into trying to get those estimates correct. The source of the data is a national EPA database known as ISIS, which you may be familiar with. It's a large and detailed database, but there's a fair amount of inconsistency in reporting, and data are often missing or incorrect. So we put a fair amount of effort into working with the states and sometimes the facilities themselves to fill out that database where possible, using a variety of different methods. One of the most important aspects is getting the locations right, because if a point source is located incorrectly upstream or downstream of a monitoring site, it'll cause a large error in the model. And so we went through and checked many of those locations. And this is just kind of an indication of the procedure we went through. We took imagery, overlaid the network data with the lines, and the red lines are the catchment boundaries, and actually found the facilities and made sure they were located on the correct stream and the correct catchment. This one is pretty straightforward, but we found many that were largely incorrect in location. So we had to do a lot of detective work to track those down and locate them correctly. In the end, we did a complete accounting of all the major facilities, including all the SIC codes, and we included a significant number of minor facilities as well, focusing mainly on the wastewater treatment plants. Okay, so I'm going to shift gears again, going from the databases to model results. Just wanted to give an initial indication of what we're seeing in some of the models. Now, I thought that starting out with a water balance model might be of interest here. So I'll give a little description of what we saw there. This is just a list of the variables that we found to be statistically significant nationally for predicting stream flow in streams. Starting out with the sources of water to streams, runoff, as anyone would expect, was by far the dominant source of water to streams. That's defined by precipitation minus evapotranspiration. Some people call it excess precipitation, but that's the main source. But others that were also significant and pretty consistently significant were wastewater discharge. In all regions, that was a important variable. Spring flow was also important in most regions, and then transfers, mostly in the western regions, were statistically identifiable as well. That includes transfers across watersheds as well as within watersheds. Delivery of water from the land surface to streams, there were a number of variables that were important there, and it really depended on what region you were in as to what variables were important. But categories of variables included vegetation. The greenness or density of vegetation was important in some regions. Temperature was important in some regions. And soil characteristics of one form or another were important in just about all regions. And then there were a variety of others that were important as well. Loss from the streams themselves, the reservoirs were the most important. They were important in all regions. Presumably that's due to a number of loss factors, including evapotranspiration from reservoirs, loss to groundwater from reservoirs, and also potentially some withdrawals that weren't accounted for otherwise. In the western region, we also saw losses from streams as important, so that many of the streams there were losing streams to groundwater, or losing water to groundwater, and that was detectable in the models. And then two types of withdrawals were detectable. One was public supply. That was true in most regions. And then in the West in particular, irrigation was an important loss factor. So this is a very preliminary, hot off the presses result of the model predictions for water in the Southeast. On the left here, this is the local contributions to stream reaches. And then the one on the right is the same, only it's the amount of that that gets to the final receiving water, which in this case would be the ocean or the Gulf of Mexico. And what you see here is that the maps look very similar, which implies that most of the water that gets to the streams makes it all the way downstream, and that losses along the way are not a major factor. There are a couple of areas, though, where you can see a difference. If you look in the central part of North Carolina and compare the two maps, the Apalachicola in southern Georgia and northern Florida, and also in the Tampa area, there are differences between the delivered and the local yields. I think the reason in all of those cases is due to a combination of reservoirs, the presence of reservoirs, as well as some type of withdrawal, public supply primarily. So this is just one indication of what the models can show. I thought that might be of interest from the supply perspective. What we did with this information, now that we've done it for the water balance models, is that we're incorporating the same information in the water quality, because some of those losses also relate to the loss of mass. And so we want to account for that in the water quality models. Shift gears again. This is getting into the tools aspect. This is just a website that we have. You can go to this link. I won't go into it just for the sake of time. But if you click on this map in any of these regions, it'll come up with a set of drainages to major estuaries And if you click on those drainages, you'll get a variety of different types of information on the nutrient loading to those estuaries to see what is driving things in each of those. That's something that's available now and that you can explore at any time. We have new mapping tools, which I'll give an example of here. We built a total dissolved solids model. This was published back in 2014, and that's been available for a while now. I thought I would use it as an example for the mappers because I thought it would be the most relevant here. Now, I'm just going to focus on the mapper itself. Please feel free to take a look at the report to get more details of the TDS model. So the mapper, and we have these for all of the models. So as we release new models, we'll have one of these for each of those. What it allows you to do is, first of all, map a variety of different types of predictions. The one indicated here is the incremental yield. So this is the local yield to each reach. And then you can hone down on things in a variety of different ways. The first is that you can select an area of interest, state or watershed at a number of different scales. This is just one example I did for the Ohio drainage, but you can also do it on a watershed basis too, for the Ohio River Basin. You can group the results by different units. These are the catchments, which is the smallest unit that we have for predictions. But you can also aggregate by other watersheds, things like, in this case, Huck 8s. Once you do aggregate, you have the option to generate some charts and tables to summarize the results. This is one bar chart showing, it's a stacked bar chart. So it shows the yield from each of these watersheds, broken down by the source contribution for each of those. You can come to the bar chart and click and drag across those bars, and it will zoom into those bars so that you can see them better. And there you can see how the sources are broken out for each individual catchment. As you hover with the mouse over each one of these, it will highlight on the map. So what I did was I highlighted on the tallest bar, and that highlighted the Youngstown area, Huck 8. And you can see from that the largest contributor to total dissolved solids in that area is road salt, which probably makes sense given the lake effect snow that occurs there. So those are just some of the things you can do. I think the best thing to do is actually go to the website and explore on your own. It's very intuitive and it's not hard to figure out at all. If you go to the Sparrow website, I'll give the link in a second here. There are a number of mappers available there now, which you can explore. This one is not quite available yet. We expect to have it in the next month or so. And that should appear on the website as well once it's ready. A couple of other models, which I'll just touch on, are ones that were designed to map benchmark exceedance probabilities in a spatial context. The first one is based on a model called WARP, Watershed Regressions for Pesticides. And that model was designed to estimate pesticide levels at watersheds throughout the country. There are models for a whole range of pesticides available. If you go to the website there is a mapper system there like this, where you can do similar types of maps, but for a whole range of pesticides. And then another option is to look at benchmark exceedance probabilities in groundwater. This one is for manganese, and it's based on redox conditions in the Central Valley of California. And it has it broken out both by domestic wells as well as public supply wells. And you can see where exceeding benchmarks has a relatively high probability throughout that region. I'd recommend going to this publication if you want more details. That is available now. And that's all I'll say. This is the link for the Sparrow webpage. If you go there, you can get quite a bit of information on Sparrow, as well as be able to access all of the mappers that we have available right now. And I'll leave it there.
Great, thank you so much, Steve. So I am going to come back to my screen here, and I just want to remind everybody to please type in your questions. And I also wanted to remind everybody about a handout that ASWA developed, and along with a web page on road salt and drinking water. So the web link is here on the screen. The web page and the handout both talk about the intersection of roads and drinking water, about how state drinking water programs and state highway programs can work together to reduce impacts from road salt on drinking water sources. And then, as you see here, it also includes a table with information about impacts from road salt based on each element of the multi-barrier approach to ensure safe drinking water. So you can go to the web page, and there's a handout that you can download. It's one page front and back. It's good to take to meetings and things to just share information and try to work with partners on reducing impacts from road salt. And it also, there's also a webinar recording from back in March that we did with the American Association of State Highway and Transportation Officials, with representatives from New Hampshire and from Maryland about what they're doing in their states to work across programs. So I just wanted to remind everybody that that's available. And then if you can go ahead and type in your questions, and I can turn it over to Patty Tocolino here from USGS.
Hi, everybody. This is Patty. So we've got a couple of questions that have come in. The first is directed primarily at Ted, I think. So this person is running a roundtable on source water challenges of some NGOs in the Baltimore area, and was wondering if we have anything that boils down the work into just a few slides or a one-pager. So Deirdre just showed a really great resource that ASWA has on their website, and we're wondering here if there's additional resources, Ted, that you'd like to direct people to.
Yeah, that's a good question. I mean, there's the paper for sure, and then, as I said before, there's the trends mapper you can look at. I guess it depends on what the nature of the actual question is, and whoever posted that question. If you want to get in touch with me, I'd be happy to work with you a little bit on and figure out what it is that you're looking for. But I will say that the Baltimore area is one of the areas where a lot of work like this has been done. As I mentioned before, Sujay Kajal is at the University of Maryland, and he works with the Baltimore LTER, the urban LTER that's there. And so he may have something that's more specific to Baltimore if that's what you want. But if you want something that gives you a broader scope, I'm happy to work with you on that.
Great, thank you, Ted. I did chat him your email address so he can contact you directly.
Thank you.
We have one other question that I think is primarily aimed at Ted, but I'll open it up to both of you guys. How would we know if our local area is doing enough to deal with this issue? And by this issue, I'm assuming corrosivity or potential corrosivity.
Yeah, I mean, I guess what's that saying? The proof of the pudding is in the eating. I mean, if you're not getting action level exceedances, then it's a pretty good way to understand that they're doing something about it. In terms of controlling road salt, I don't know. It's a catch-22. I mean, this is a question I get a lot when I give this talk, which is what can we do to control road salt inputs? And the problem is, putting salt on the roads in the wintertime is also a human health issue. I mean, if you don't do that, my guess is that the frequency of accidents would go up, and that's also a risk to human health. There are not really good alternatives to road salt at this time. Anything else that's been tried has its own environmental side effects. In some places they use some sort of an acetate, it's like sodium acetate or something like that, and it, as you can imagine, as that gets into surface waters, it causes BOD problems and things. So really, in terms of managing salt, the best thing you can do is to just be smart about its application. Timing and intensity of salting means a lot, and if you do that properly, then it's that can work better, and that has been shown to be effective. But beyond that, there's not really a lot you can do to just stop salting in the wintertime. But if the question is really more about the action level exceedances or about lead contamination, really the best tool you have right now are the action level exceedances put in place by the EPA, unless the state does something extra, which is the case in New Jersey.
And I would say the only way to really know is with monitoring. So it'd be interesting to see what's being done in that regard as far as monitoring drinking water.
Yeah, and this is Deirdre at ASWA. I'll just repeat Ted's message about public safety with road salt and balancing that. And I think when we had our webinar back in March, that was one of the things that came up, and the state highway programs, I think, are doing a really good job at doing sort of precision applications with brine, and they've got monitors on their trucks where they can see the road temperature and that sort of thing. But to go above and beyond for road salt applications, you could look to the New Hampshire example where they actually have a certification program for local applicators of road salt, so looking at sidewalks and parking lots for office buildings and schools and that sort of thing, so that even private companies that apply road salt are doing it in sort of a way that ensures that they're following best practices, that aren't over applying salt when it doesn't need to be.
Yes, thank you, and thanks for the great questions that came in. That was the last question on the list, so if anybody has another one, type it quick. Otherwise, I'll turn it back over to Deirdre.
Okay, great. Thank you, Patty. And I just want to thank our presenters today and thank everyone that joined us for the webinar. Just a reminder that we will have a recording available on ASWA's website in the next week, so you can go back and view it later. And then if you do have any other questions that weren't answered, you can always send them to us, and we'll try to answer them after the webinar. So thank you very much. And with that, we will end the webinar for today. Thanks again.
Thanks, everybody.
Thank you.